Hello everyone. We are Lakshan, Madhav, Ramesh, and Muralidharan from the Department of Computer Science and Engineering at Sri Venkateswara College of Engineering, Chennai. This project was carried out under the guidance of our mentor, Dr. S. Purani, Assistant Professor in the Department of Computer Science and Engineering. In this project, we propose a privacy preserving generative machine learning framework for synthetic medical data generation. The main goal of our work is to generate realistic healthcare data while protecting sensitive patient information and maintaining machine learning utility. Machine learning is playing a major role in modern healthcare, especially in areas like disease prediction and clinical decision support. But building reliable machine learning models requires large amounts of patient data, and that creates a serious privacy challenge. Medical records contain highly sensitive information, and sharing this data is heavily restricted by regulations such as HIPAA and GDPR. Traditional methods like anonymization and masking are often not enough because important statistical patterns can still leak sensitive information or reduce the usefulness of the data. To solve this problem, our project focuses on generating synthetic healthcare data that preserves the statistical properties of real patient records while protecting patient privacy. One of the biggest challenges in this project was generating realistic medical data while preserving the complex relationships between clinical features. Traditional GAN architectures are mainly designed for images and often struggle with structured tabular data sets that contain both numerical and categorical values together. Medical data sets are especially difficult because many clinical features follow irregular or highly imbalanced distributions. For example, measurements such as cholesterol levels or blood pressure may contain multiple peaks and strong correlations with disease related attributes. To handle these challenges, this project uses conditional tabular generative adversarial network, which is specifically designed for tabular data generation. During training, the generator learns the statistical structure and feature relationships present in the original healthcare dataset, while the discriminator continuously evaluates whether the generated records resemble real patient data. CTGAN also uses conditional training to better handle class imbalance, allowing the model to generate more balanced and realistic synthetic records. This makes it well suited for privacy preserving healthcare data generation. The complete workflow begins with raw healthcare records entering a secure processing environment where the data is cleaned and prepared before any machine learning operation takes place. Since medical records contain highly sensitive patient information, the first step focuses on protecting the data by removing direct identifiers, handling missing values, and applying encryption and integrity verification mechanisms to maintain security throughout the pipeline. Once the dataset is processed and de identified, it is passed into the CTGAN model for training. The model learns the statistical relationships between the medical features in the dataset, including both numerical values and categorical attributes. Using these learned patterns, the generator creates entirely new synthetic patient records that resemble the original dataset statistically, but do not correspond to any real individual. After the synthetic data is generated, it moves into the privacy evaluation stage, where multiple validation checks are performed to measure potential information leakage. Attribute inference attacks are used to determine whether sensitive patient information can be predicted from the generated data, while statistical tests such as the Kolmogorov-Smirnov test and Jensen-Shannon divergence are used to compare the similarity between real and synthetic feature distributions. If any privacy metric exceeds the predefined threshold, the generated dataset is rejected and the model must be retrained. Only the datasets that successfully pass all privacy checks move into the final validation stage. Here, the utility of the synthetic data is evaluated using machine learning models such as random forest, Hest gradient boosting, and logistic regression. The system compares the performance of models trained on synthetic data against models trained on real data to measure how much predictive capability has been retained. Representation level similarity checks are also performed to confirm that the synthetic data preserves the overall structural patterns of the original dataset. Finally, only the datasets that satisfy both privacy and utility requirements are approved for controlled release. Generating synthetic data alone is not enough because the system must also ensure that the generated records are both privacy safe and practically useful for machine learning applications. To evaluate privacy, the generated data sets undergo multiple validation checks designed to measure potential information leakage. One of the key evaluations used in this project is the attribute inference attack, where a machine learning model attempts to predict sensitive patient information using the synthetic data. Lower attacker accuracy indicates better privacy preservation. In addition to this, statistical similarity tests such as the Kolmogorov Smirnov test and Jensen Shannon divergence are performed to compare how closely the synthetic feature distributions match the real dataset. These metrics help verify that the generated data preserves realistic statistical behavior without directly exposing real patient records. Once the privacy evaluation is completed, the system moves into utility validation. Here, machine learning models such as random forest, has gradient boosting, and logistic regression are trained separately on both real and synthetic datasets. Their performances are then compared using metrics like accuracy, precision, recall, and F1 score. The framework also performs representation level similarity checks to confirm that the synthetic data maintains the structural relationships present in the original dataset. Finally, only the datasets that successfully satisfy both privacy and utility thresholds are approved for controlled release. The implementation begins by loading the UCI heart disease dataset into the secure processing environment. At this stage, the system reads the raw healthcare records and checks the structure of the dataset, including the number of rows and features available before preprocessing begins. Before any modification is made to the dataset, a SHA 256 hash is generated. This hash acts like a digital fingerprint for the original data. Later in the pipeline, the hash is recomputed and verified again to ensure that the dataset has not been altered or corrupted during processing. Once integrity verification is completed, the dataset is secured using a hybrid encryption mechanism. A ES256 GCM is used to encrypt the actual healthcare data efficiently, while RSA 2048 is used to securely protect the AES encryption key. This combination provides both strong security and practical performance for handling larger data sets. After securing the dataset, direct patient identifiers such as the ID column are removed before any machine learning operation begins. This de identification step ensures that the generative model never has access to personally identifiable information. The pre processing stage then handles missing and incomplete records within the dataset. Features containing excessive null values are removed, and the remaining data is cleaned and standardized to improve the quality of training for the generative model. The original dataset contains multiple heart disease severity levels, which creates a strong class imbalance problem. To improve training stability, the target labels are converted into a binary classification problem representing disease presence and absence. After pre processing, the class distribution becomes significantly more balanced, providing a more reliable learning signal for the CT-GAN model. With the data set now securely processed, cleaned, and balanced, the pipeline moves into the next stage, where CT-GAN is trained to generate synthetic healthcare records. After pre processing, the cleaned data set is passed into the CT-GAN model for training. Here, the training configuration is initialized with parameters such as the batch size, embedding dimensions, conditional vector size, and the number of training epochs. These parameters control how the generator and discriminator learn the statistical structure of the healthcare dataset during adversarial training. During training, the generator continuously attempts to create realistic synthetic patient records, while the discriminator tries to distinguish between real and generated samples. Through this adversarial learning process, the model gradually learns the relationships between medical features, such as age, cholesterol levels, blood pressure, and disease related attributes. The pack mechanism is also applied during training to improve stability and reduce the risk of memorizing individual patient records. Once training is completed, the generator produces entirely new synthetic healthcare records based on the statistical patterns learned from the original dataset. In this implementation, three synthetic datasets are generated at different scales to evaluate how well the framework performs across varying dataset sizes. Although these records statistically resemble the original patient data, they do not directly correspond to any real individual. After generation, domain constraints are applied to ensure that all medical values remain within realistic clinical ranges observed in the original dataset. This step helps prevent biologically unrealistic outputs and improves the reliability of the generated synthetic records before privacy evaluation begins. With the synthetic datasets successfully generated and validated, the workflow now moves into privacy risk evaluation to determine whether the generated records are safe for release. Once the synthetic datasets are generated, the next step is to evaluate whether they leak sensitive patient information. To test this, an attribute inference attack is simulated, where a machine learning model attempts to predict sensitive attributes using only the synthetic data. The attacker accuracy and attack gain values are then measured to determine how much information leakage is present. Lower values indicate stronger privacy preservation. As shown in the results, all generated datasets remain below the predefined safety thresholds, indicating reduced privacy risk. The framework then performs statistical similarity checks between the real and synthetic datasets using the Kolmogorov-Smirnov test and Jensen-Shannon divergence. These metrics measure how closely the feature distributions of the generated data align with the original healthcare records. Lower KS and JST scores indicate stronger distributional similarity, confirming that the synthetic records preserve realistic statistical behavior without directly replicating real patient information. The feature distribution plots provide a visual comparison between the real and synthetic datasets across important clinical attributes such as age, cholesterol levels, maximum heart rate, and ST depression values. The strong overlap between the curves demonstrates that the CTGAN model successfully preserves the statistical patterns and feature relationships present in the original healthcare data. Finally, all privacy evaluation metrics are combined into a unified decision framework. If any metric exceeds its predefined threshold, the generated dataset is automatically rejected. Otherwise, the dataset successfully passes the privacy gate and moves forward into utility validation. In this implementation, all generated datasets successfully satisfied the privacy requirements and were approved for further evaluation. After the synthetic datasets successfully pass the privacy evaluation stage, the next step is to measure whether they remain useful for real machine learning tasks. To evaluate this, multiple downstream classifiers, including random forest, ist gradient boosting, and logistic regression, are trained separately using both real and synthetic datasets. The models are then evaluated on the same held out real test dataset to compare their predictive performance. The evaluation results show that models trained on synthetic data achieve performance levels that remain very close to models trained on real healthcare records. Metrics such as accuracy, precision, recall, and F1 score demonstrate strong retention of predictive capability across all three synthetic datasets. Among the evaluated models, logistic regression showed the smallest performance gap between real and synthetic training, indicating strong statistical consistency in the generated data. The framework also calculates a utility acceptance ratio, which measures how much predictive performance is retained when switching from real training data to synthetic training data. In this implementation, all generated data sets retained more than 90% of the original predictive performance, successfully exceeding the required utility threshold. Finally, representation level similarity checks are performed using PCA based embeddings to confirm that the synthetic data sets preserve the structural relationships present in the original healthcare data. After combining both the privacy and utility evaluation results, all generated datasets successfully satisfied the framework requirements and received approved status for controlled release. In conclusion, this project demonstrates how synthetic healthcare data can be generated in a way that balances both privacy protection and machine learning utility. By combining secure pre processing, CT GAN based synthetic data generation, privacy risk evaluation, and utility validation into a single framework, the system is able to generate realistic medical records without directly exposing sensitive patient information. The final results show that the generated datasets successfully preserved strong statistical similarity and retained high predictive performance across multiple machine learning models. Overall, this framework provides a practical and scalable approach for privacy preserving healthcare data sharing and machine learning research. Thank you.